Okay, so let's continue. So as I told you, we are not going to cover the proof of Artin's weak approximation theorem, but I do need it, and I want to state it, and it appears in a video, like a 1-hour video that I recorded, and you can see the proof if you want, or you can look at the notes, if there are notes of that. But let me tell you what the theorem is, because we are going to need it today at some point, and many times. So let's say now that you are given n valuations, okay? It's even before the context of a function field, by the way. So this is just a valuation of a field. It appears as a unit before function fields. So these are non-equivalent valuations. Okay? And I'm also going to assume that they are onto. So you see I'm only taking discrete ones, because we know that in function fields they are going to be discrete. But here I'm not assuming anything about function field or not. I'm just taking valuations that are mapped to Z and in fact onto Z. If not, we can just normalize. Maybe I'll close the door. Okay. And let A1. And let A1, so say you're given n functions and m numbers. Numbers, I mean elements in the range, in the ordered group. Then what Artin's approximation theorem tells you, it's really an interpolation theorem. It tells you that there exists a function in your field such that for every I, the valuation of xi minus ai is mi. Okay, so it tells you, if you are given n valuations and this is n prescribed functions that you want to kind of get close to in a sense, and n numbers that describe how close do you want to get to those functions, then there is a function that does that for all of them simultaneously. So there is a function such that the valuation of the ith valuation, applied to x minus ai is exactly mi. And I didn't tell you here, but I told you that in the video that there is a relation. I mean, when v is large, you should think of it as, v of some v of x minus ai in this case. Saying that this is large, even though mi could be negative really, but saying that this is large is really saying that there is some absolute value for which this is small. Okay, in a sense. So there is a way to cook up an absolute value for evaluation. It's not important for us, I'm just saying that. And so when you see vi of x minus ai equals like 100, it kind of means that these two things are very close with respect to the I metric that you get. Okay, and so that's why it's called an approximation theorem. You want to get close to some extent to some given functions by one function, and you can do that in all matrices, like, how do you say, like metric in plural? Matrices. This is matrix simultaneously. Which kind of mean, and of course, assuming they're non-equivalent, otherwise you cannot do it. So they are not like one multiple of the other. That's really what it says. And so this means that really they really are independent. You see, it's like, for example, you know that in numbers, like you have a valuation for every prime, and you can cook up numbers that modulo 2 to the k and modulo 3 to the m are close to what you want. 2 and 3 don't interrupt each other. And for valuation in general, that's also the case. Okay? So that's a theorem. It's not trivial. See, there is a very nice history about all of these things. Maybe I'll talk about it a little bit when we talk about the zeta functions. And Artin was one of the pioneers there. Yes.
X minus AI is n is large, which means close.
Yeah, exactly. So when m is large, so the relation between, so the absolute value, the way to define it is, I can just tell you, So the way you define an absolute value given a valuation, and then you can apply it to a difference, but it's just 2 to the minus the valuation of x. 2 is an arbitrary choice, but let's stick with that. So there is so it turns out that this defines an absolute value, like the triangle inequality here translates to something that's even stronger, but definitely sufficient for the triangle inequality here. You see 0 goes to, valuation of 0 is infinity, so this is kind of 0 in a sense. So the absolute value of 0 is 0. And if you take a product here, it goes to a sum, and then you get that indeed the absolute value of AB is the absolute value of A times the absolute value of B. So it actually does define an absolute value. It's called, it's actually a stronger one because the triangle inequality is stronger. But yeah, you get a triangle inequality like that, and you see when this is larger, this is smaller. So that's why it works like that.
Every function x can be approximated.
Exactly. No, so every n functions, for every n function that you give me, and any described approximation parameters, so regardless of what n valuations or absolute values you take, you can find one function that approximates all of them simultaneously, as you wish.
One function.
Right. Yes. Only on the point. Yeah, it's very much related to that, and Chinese remainder theorem also kind of pops to mind when you see these things. It's all related, and it's amazing that it's called the weak, right? How stronger can you make it? But you'll make it stronger. As you said, it's only on those points. X can behave, in a horrifying manner outside of these points, and the strong approximation theorem tells you that you can make sure all the poles are at one point, which you'll need at some point. But that's I think that requires Riemann-Roch. That requires more tools, and that's kind of elementary to prove. But it's an hour, like in the video, with no questions, and I talked fast a bit. So it's not trivial at all. And if you want to really understand valuations, like working with valuations, you should look at this video. It's like the art of working with valuations, cooking up functions that are valuations like this. It's not trivial at all. But we're going to use it as a black box, okay? Okay. So yeah, that's now the, like in a sense, last unit that is building up stuff that are elementary, like points, function field, like the basic stuff, before even talking about the deep stuff about them. But there is some of part of unit 11 which is also like that, so I don't know. So let's see. But the unit called is divisors and Riemann-Roch spaces. Maybe when we'll get a bit tired, I can tell you about some history. It's really interesting. It's like weirdly developed. Yeah. But not now. Now we have some power. So definition 1. By the way, it was essentially 100 years ago. Like Riemann was before, but Artin, for example, worked in the 20s. So it was 100 years ago. Like 21, he published one of the first papers and so forth. So it's really kind of celebrating 100 years. But Riemann was like 50 years or something before that. Okay. So let f over k be a function field. We are going to work in function fields all the time now. A prime divisor, sometimes people just say prime, but that may confuse us with prime ideals. For no good reason, by the way, because we're not going to see prime ideals. So I'm just going to say prime divisors all the time. So it tries to generalize primes. Okay. If you do algebraic number theory, these are the primes that you have in the number fields. So, but a prime divisor, and it's like Gothic P, but I don't know how to do it. It's like, it has all of these, like this. And I want people to like do it again. Like, without disrupting everything. So I'm just going to write P. A prime divisor P of f over k is, and that's going to summarize everything we did so far essentially, congruence class of places of f over k. Okay, so a prime divisor, okay, so a prime divisor, maybe last time or something. So a prime divisor is a congruence, just kind of a remark. That's the definition and that's it. But a prime divisor is a congruent class of places, which usually denoted by phi. And we said that like really phi doesn't, a particular phi doesn't encode information which is interesting. This is the interesting information. Like the degree of a place is a property of the class and so forth, and the residue field and so forth, right? So you care about these, and these are in one-to-one correspondence. That actually we did prove, I think, with OP, with the evaluation ring, which is in one-to-one correspondence with the maximal ideal. These are also like, this is Gothic and this is Mafcal or something, I don't know, you can see in the notes. And this is in one-to-one correspondence with a congruent class of valuations. Right? So we have these, I mean, these are the good objects, and these are like kind of annoying, nice to work with, but annoying because you need to talk about the classes all the time. So Stirtonov uses this as the notion of a place, for example. And we used that one as the notion of a place. So if you read it, then you read carefully. But anyhow, a prime divisor is just all of this. Right? And we denote, turns out that these are the primes. These are the things you want to factor. As I told you, there is no unique factorization in the rings that we are going to work, but there is a unique factorization of ideals, and the factorization is going to be to these ideals. So that's kind of what's going to happen. That's the way you kind of fix the fact that you don't have unique factorization. And much of this is due to Dedekind, and this is called the Dedekind domain if you add some restrictions that we have. And I can't talk about it because we don't have the background. So, but keep in mind, these are important definitions, and we denote by like this kind of cool P. Sometimes you write the function field, sometimes you not. The set of all prime divisors is a prime divisor of f over k. I'll explain why it's called a divisor in a second also, but prime divisor. Okay, so finally, like all the 4 and 1/3, or I don't know, lectures so far were like maybe at least 2 of them were 3 were really about this part, and now we understand it. From here on, we call all of the things that we did a prime divisor for every particular valuation or so forth. So in number theoretically, you think of these as numbers, like prime numbers. In algebraic, geometrically, you think of them as points. And it's a philosophical question of whether it's us dividing like geometry and number theory, or is it like something, it's kind of the same. So you can think of as the prime numbers as points if you want, and you can think of as points as prime numbers in some ring and so forth. And a remark, we proved that all valuations in VP, so in Fick is a prime divisor, namely, a valuation ring, for example, and look at the class of all valuations corresponding to P are discrete. Actually, yeah, we proved that they are discrete, and yeah. And actually, there is like a lambda that maps one to the other because valuations are equivalent, even if and only if there is a order-preserving group isomorphism between them. So in our case, it's just multiplying by some factor because everything is, we know that all of them are discrete. So maybe one of them is V and the other is twice V. But you don't have minus V, by the way, because it's not order preserving. And what I want to say is that we pick, because we don't want to work with these congruence classes, we pick the unique valuation, I mean, given a prime divisor in VP that is onto Z, right? There's exactly one of those. All of the rest are stretching of it. And denote it by VP. It got to be DVP. And what I'm saying is that if you say fix a place and look at the congruous classes of valuations that correspond to it, or really to the congruence classes of places, or if you fix a maximal ideal and so forth, or valuation ring, then these are going to, as we proved, these are all going to be discrete because it's a function field. And because they are discrete, one of them is onto Z. I mean, once you have valuation here, you can always, if you have like 5Z, you can just shrink by one over a fifth. It's going to be a valuation still, so it's onto, so it's here. It's not that it's not here, it's here. And that's going to be noted by VP without these brackets, right? It's not, like this. A VP that without this bracket. So, right, so VP is from F to Z, it's trivial on K and trivial on F, but it's onto. So I don't know, sometimes people write it like that. Okay. So it's onto Z. Questions? Good. It's unique. No, because we said that, right, so two valuations are equivalent if there is an order preserving isomorphism between them. So in Z, when we talk about discrete ones, it means that one is a multiple of the other. And so it means that it's unique. But really what happens is just normalize. Like you take a valuation, look what its smallest value, like positive smallest value, and divide by that value. It will take some time until we see examples, but that's what we'll do. Okay. So another definition. So if these are the primes, now I want to define the numbers. Okay? From the primes. Right? It's usually the other way around. You have the numbers, and then you look, oh, there is a notion of a prime. But here it's you start with the primes, and then you go to the numbers. And actually, I'm going to be a bit, I'm going to also define like infinite numbers, but in the wrong way. Not like a good, like Cantor way, infinite. Like it's like a temporary way that we are going to fix later. So let f over k be a function field. We denote by, so D for divisors, f over k. But I'm going to put a tilde here because it's going to be a temporary definition. We are going to need it for 2 lectures, and then we are going to be able to remove it. But for now, we are going to still need it. So this is, by whom? The set. It's not going to look like numbers, but I explain why these are numbers. The set of formal expressions of the form. So you sum over all places, all prime divisors. Sorry, sometimes you call it places because it's the same thing, but over all prime divisors in your function field. At some point, you will prove there are infinitely many of them, but so it's a big sum. You have a number. That's a number in Z. Could be negative, but it's an integer times P. It's a formal expression. So these P's are just like sitting there. You have like 5P minus 2Q, something like that, where NP is in Z, as I said, and that's it. Okay, let me dwell on it for a second. So the elements in D hat, F over K, are called pseudo divisors. Okay, pseudo means it's kind of, we don't feel comfortable with them. And sometimes you don't write it like that. Sometimes you write it like in number theory, usually you write it like that. You write it in multiplicative form. It's the same thing, just another way of writing it. But when you do that, you can start seeing, oh, this is a number, right? I mean, at least if all of them are, if there are only finitely many products here, finitely many p's for which this is non-zero, then it's a number, right? You take the product of some primes. Maybe these are negatives in some cases, so it's like over a product of some other primes. So these are like the rational numbers in a sense. Right? At least if you think of these as primes, and these are just how many times that prime appeared there. So in number theory, algebraic number theory usually work like that. And they are called divisors because you see it, if you have one of these and another, you think of like P as dividing that product. You can look at one expression like that and another, and you can ask if it divides the other, namely if the powers of P here are smaller or equal than the powers of P there. So that's why it's called a divisor. In number theory, it looks like that. In algebraic geometry, it looks like that. Because I don't know exactly why. I mean, this gives you better the impression that this is a billion, really. Like, well, it's a group. We're going to talk about it in a second, but no. So far, they're right. So far, that's the notion of a pseudo-divisor. For divisors, I'm going to say finite. So pseudo-divisors are kind of weird. You have like infinitely many primes factoring you. And divisors, which I'm going to define next, are those for which all of the NP byte finitely many are 0. But we are not going to use this notation, okay? So this one. But I don't know. I think it's good to know that. And so also know that some remarks. Yes.
What does it make sense to cases?
Yeah, good. So that's exactly this. Know that the tilde, like the pseudo divider, is a group via component addition, component-wise addition. Or in this notation, component-wise, like product or addition in the exponents. So it's like multiplying, right? When you look at it like this. But like, so if you write a number, if you write 6, or maybe if you write 12, usually you write 2 squared times 3. But another thing you can write is twice the prime divisor 2 plus 1 the prime divisor 3. Just as it's the same information, just you don't do that, you do that usually. But it's going to be more convenient in our case to do it like that, slightly more convenient, nothing big happening. But the thing that we are thinking of, because we are really thinking number theoretically here, you should think like that. Okay, so we ask what does it mean to add those, so it's like multiplying the corresponding numbers if there were numbers. These are not numbers. Yeah, these are prime divisors, which are places, and these are just, or at least these are formal sums of those. Formal, I mean, I give it no meaning. It's like, there is a name for it. It's the 3 abelian group generated by the prime. But really, this is what it is. You have like you don't take the products. It's not like there is no group structure or anything. You have like a prime, and every prime can appear with some multiplicity, and that's it. You can think of it also, one way to think of it is as a function from P to Z, right, if you want. For every prime, you have a number. But it's not the right way to think about it. It's like thinking of 6 as numbers as a functions from primes to Z. It's not like, it's weird, you don't do that. Maybe you do that. So so this is a group under composition, just to be sure that we understand. So if you take 2 such things, and I'm going to stop writing here from next time that we are going over all prime divisors. So if you take 2 sums like that, then you can add those. I'm defining this symbol now, right? So it's not, oh, it looks like a bitwise parity or something. I'm defining this thing. So this is defined to be a sum of NP plus NP. P. Right, this is a number also in Z. And one more thing about this. we are going to do something which doesn't look confusing, but it is. So now I want to have an operator that takes something like that and a place or a prime divisor and extracts the coefficient, like in the generating function. It's not confusing. The name is confusing. So for Q, if you take a particular prime in f over k, we define a map VQ, which looks like the valuation of Q, but it's not, okay? So it has a different type altogether. It takes a prime, it takes a divisor. It doesn't take a function. VQ, the usual VQ takes a function and tells you, give you a number in Z. So VQ takes a prime divisor and just extracts the coefficient of Q in the divisor. So VQ of any divisor that you give me, and any divisor looks like this, we just spit out NQ. Okay? But it's the same name, which is confusing. It's confusing because, like VQ, okay, so I just want to stress the confusion, so it won't confuse you. Maybe it wouldn't have if I wouldn't even say that. But so VQ usually takes a function and produces an element in Z, union infinity. Just this is the plain old VQ. And what can you say about VQ of sum of two functions?
The original case?
Yeah, the original, right, good. Exactly. Right, you have this triangle inequality. It's definitely not the sum. The product goes to the sum, right? So actually, VQ of x, it's a homomorphism. But here, it does go to the sum, right? So VQ of, if you take two divisors, it's like, usually this should be a gotic A and this should be a gotic B, but I don't know how to do it. So actually that thing extracts the coefficient of Q in the divisor, which is the sum, which by the definition of sum, component-wise sum, really is VQ of A plus VQ of B. Okay. So there is a sort of confusion a little bit here. VQ is the same name, and it's good it's the same name. You'll see later why, but it's the same name, but it behaves differently when you give it a divisor or give it a function. It's not a valuation. It's an extraction. Just give me, like, just tell me I want to refer to the number that kind of is the coefficient of Q. It's not a valuation. It doesn't take a function. It takes a divisor. And at this point, there is no relation between divisors and functions.
If you like it like that, like it makes more sense.
Interesting. That's actually nice. The valuation of their product will be the sum. Right. So at least you're right. At least when you write it like that, the correspondence is clear, and then you don't expect any correspondence here. Right. Yeah. Good. Yeah. Actually, that's a good. Right. So yeah. So that's one bad reason of using this notation. All right. Interesting. I didn't think about it. But we will work this a billion additive notation. So it may confuse you. It will confuse you at some point because we are going to also define a divisor from a function, and then it's like, who are you talking about? Like the VQ of the divisor coming from the function or the VQ of the function? And okay. Some other remarks. We define partial order, like a partial order on D tilde on the pseudo divisors in the natural way, just component-wise comparing them. So A is smaller or equal than B, so I want to define this if and only if in every coordinate for every prime divisor. So the number that the coefficient of P in the A is smaller or equal than the coefficient of P in B, and I'm using this notation of extraction to write it like that. See, it's very convenient because you don't have to always write the divisor. You can access the coefficients without writing the divisor. That's what's written here. Right, that's why this is convenient. You can write VP of D or VP of A without writing the entire sum and say NP. Right? It's like just convenient. So by the way, this is a partial order. It has nothing to do with ordered groups, which are total orders and so forth. And in terms of, by the way, so maybe continuing your remark, if you look at the this kind of notation, then smaller or equal, what does it correspond to? Divides, exactly. Because so if this is A, and there is another B, saying that this is smaller than B, says that this is smaller or equal than every corresponding element there. So you have, for every prime, you have less of it appearing here than there, or equal. So it's really division. Good, so this is why, right, and when a prime divisor is larger than the zero divisor of all zeros, it's like a number, not a quotient of numbers, like an integer, because you don't have primes with negative coefficients. So we will write something like this usually. This is just a divisor, it's all the zero divisor. This means that P always appears with non-negative NPs, every P appears with non-negative, which means that this is like a number in a ring in a sense, not in a field. Like you don't have 1/. But okay. Also, you can define the max and the mean. So the max of two divisors, because you have partial order, so it induces a max and a mean, like generally, but let me specify exactly how. So you just take for example, for the max, you just take the max of the two corresponding valuation. Right, per P. You look at every prime divisor. It has 3 in one, 4 in the other, you take 4. No, it's not every. Yeah, I just had a discussion about it, and then there is no content in note I wrote. Yeah. Maybe besides the fact that note there is a zero divisor. So this just takes the max of the primes. What does it correspond in this notation? LCM, right? Because you take the minimum you need to make sure that it's divisible by both, right? From each prime. So what is this? This is exactly. So I mean, we will see those, and it may be a little bit weird what do they mean, but they actually mean the LCM and GCD essentially. And also just note, I mean, it's obvious, but I don't know, just let's record that there is a, like in ordered groups, but it has nothing to do with ordered groups because of the partial order. The order respects the addition. And you just add stuff, so same number goes, even if it's negative, same number goes. So nothing changes. Questions? Okay. So let's define the notion of a divisor, which is just a pseudo divisor, but with finitely many NPs that are non-zero. This is the main thing that we want to talk about, but we won't be able to talk about them because we won't know things are finite until we prove it, and we can't prove it without having a notation to talk about it without knowing it's finite. You just need it for a couple. It's like a labor that you'll have to do initially. It's very characteristic of this field that you have a definition that goes away. Okay. I wonder if there is a reduction, like for every proof with vanishing definitions, there is a proof with non-vanishing. Yeah, which makes sense. Okay. So let f over k be a function field. And d tilde is, of course, the usual d tilde. I will never almost write this because, well, at some point of the course, there will be two function fields, but for now, there's only one function field. So it's always clear by context. An element, a prime divisor, a pseudo divisor, is called a divisor if VP of A is usually 0. So it's 0 for all but finitely many. P's. Right? I mean, this set is infinite. You don't need to know it right now, but it is infinite. For example, in the rational function fields, it corresponds to irreducible polynomials and infinity. There are infinitely many of those. And in function fields that are large, in other function fields, it's even more. So, but you don't know that yet. Nonetheless, a divisor is one that only uses like finitely many prime divisors. We sometimes say that this is happens almost always, like in Lebesgue notation. And the set of divisors of f over k is denoted. How would you denote it? D, right? Just remove the little, mankind because of D. Sometimes d of f over k, sometimes d. And what is the structure of this set? Like this is a group, right? So what is the structure of this set? All right, finite sums, but right. So that's why it's a subgroup, right? So it's also a group because if you so it's a subset and it's a group under the same operation because when you add two divisors with a finite support and there's finitely many primes appearing there, then it's also finite. And the zero divisor is also a divisor. So 0 has only zeros. So the unit is here. Right? The 0 is the best divisor, okay, in the sense of how many non-zeros do you have. Okay, so that's just, very straightforward definitions. I mean, if you want to talk about numbers coming from primes. And now the fun starts. Oh yeah, maybe after the break the fun will start. So I want to talk about the degree of a prime divisor. We actually talked about it already, but I just want to talk about it in this context. So let f over k be a function field. The degree of a prime divisor is, how would you define it? Exactly, you can write it like that. The degree of the residue field, which is the best way. Or you can say you can take the degree of any place that corresponds to this, but all places, this is the residue field, this is the degree anyhow. So that's kind of the best definition. Yeah, dep. Maybe it's a good symbol, but yeah. So and we extend this definition to a general divisor, but not pseudo divisor, because when we get infinities, general divisor. So the degree of A, where A is a divisor, formal sum of prime divisors, how would you define that? Like there's only one thing you can do. Exactly. So instead of NP, I'm going to use the extraction procedure. So this is NP like of A. Exactly, right? So I'm looking at the divisor. The divisor has like a number times P. And this is the number that multiplies P. So I keep the number, could be negative by the way. I keep the number and I replace P with the degree. So it's kind of the linear extension of the degree function. It's also a group homomorphism, right? Because just if you like types, so it takes an element in D, which is a group. It's a subgroup of D tilde. There is no sense in defining this on D tilde. I mean, there is a sense, but you get infinities because you add infinitely many things. So I don't want to do that. sometimes you do want infinities, but that's not the right place to have infinities. And it goes to where? Z, right. Right, and it's a group homomorphism because when you add A and B, then the degrees are added. Not because of anything like deep about that, just because VP of A plus B is VP of A plus VP of B, because it's VP of divisors, not VP of functions. So this is a group homomorphism. Okay. And it's also, just as another, it respects, what can you say if you take two divisors and you have this, what can you say about the degree? Right. You see, I give it that much attention. It's so easy. Not really worth it. I could have just not said that and used that. You said, well, but there are negatives, but it's not really important. It's not negatives. I mean, there's nothing to do with it. These are positive. So if this is smaller than the corresponding VP of B, then that also will be smaller. When you sum them, it's going to be smaller. There could be negative, but this is positive, and that's the important thing. Yeah, good. Okay. A question so far? Yeah. Why is this a good name? Right. So, I mean, I'm not exactly sure. The one thing I can tell you is that when you look at the rational function field, it is exactly the degree of the irreducible polynomial that corresponds to the place. So it really, I mean, in the rational function field, the places are coming from irreducible polynomials. And when you define that, the degree of the place corresponds to the degree of the irreducible polynomial. It's the same thing. Yes, the degree, like, right, if it's x squared plus x plus 1, it's 2. And generally, okay. Yeah.
Okay.
There is some sense, you know. Right. Right. If you have x and y's and the degree in what? In y. I mean, it's not so clear how would you talk about it, but you will see it makes sense in general. That's a good name for it. It behaves as a degree, in a sense. Right. Yeah, that's a good question. Yeah, I agree. You should, I mean, you should try to have like the intuition picture in mind all the time. And the names and notation should make sense to you, even if you don't, like, we don't yet know where they're leading.